Form the differential equation by eliminating arbitrary constants from z equals to ax square plus by square. So the given relation between three variables x, y and z is z equals to ax square plus by square. Now here a and b are arbitrary constant, and to eliminate two arbitrary constants we need three equations. So this is our first equation. So this is equation number one, right? Now we have three variables, and whenever there is a relation involving three variables, it means two of the variables are independent variable and the third one is dependent variable. Until or unless it has been differently mentioned, whenever the variables involved are x, y, and z, we treat z as dependent variable, and x and y as independent variables. And since there are two independent variables, the differential equation will be a partial differential equation, right? So how to find the other two equations to eliminate arbitrary constants a and b? That we will take derivative of equation number one. So first of all, we taking partial derivative of equation one with respect to x variable. So this will be del z by del x equals to del by del x of a x square plus by square. Now whenever we take partial derivative of this expression with respect to x, when we take partial derivative of z with respect to x, y will be treated as a constant because x and y are independent variables. So let us find out this partial derivative. Partial derivative of ax square with respect to x. So a will be a constant. Derivative of x square with respect to x, it will be 2x. B is constant. We will treat y as a constant. So partial derivative of by square with respect to x, it will be 0, right? So this is our del z by del x equals to 2ax, and this is our equation number 2. So how will we find the other equation? Now we have already taken partial derivative with respect to x. So now we will take partial derivative with respect to y. Do we have to do all these detailed calculations? No. Mathematics is all about seeing patterns, right? So we have seen that when we took partial derivative with respect to x, the result was 2ax. Similarly, if we take partial derivative with respect to y, this term will become 0, and from here we will get 2by. So we will write here similarly, seeing the pattern, we will get del z over del y is equals to 2by, right? And this is our equation number 3. Now please, already we have three equations, 1, 2 and 3. Okay, so we need not to do further partial differentiation. And from these three equations, we will eliminate arbitrary constants a and b. So how will we do it? Fine. From equation 2, we will solve equation 2 for A, right? And equation 3 for B. From equation 2 and 3, we will put the value of A and B into equation number 1, and we will get the required differential equation, right? From equation number 2, we have A equals to 1 over 2x del z by del x. From equation number 3, we will get B equals to 1 over 2y del z over del y. So we'll put the values of A and B into equation number 1, and we will get the desired partial differential equation. So putting the values of A and B into equation number 1, so equation number 1 will become z equals to, in place of a we will put 1 over 2x del z over del x multiplied by x square, plus in place of b we will write 1 over 2y del z over del y and multiplied by y square, right? This one is 2y. Now here x and one of the x will cancel out y and one of the y will cancel out. We multiply it throughout by 2 and this becomes 2z is equals to x del z over del x plus y del z over del y. So this one is the required partial differential equation which we obtained by eliminating arbitrary constants a and b from equation number 1. Okay. At times we write del z by del x by symbol p and del z by del y by symbol q, right? So this becomes in PQ symbols, this becomes 2z equals to xp plus yq. So either this form or this one, this is the required partial differential equation. Example 2. Form the differential equation by eliminating the arbitrary constants from x square by a square plus y square by b square plus z square by c square equal to 1. So we have got an implicitly defined relation between three variables x variable, y variable and z variable given by x square by a square plus y square by b square plus z square by c square equals to 1. And geometrically we know that this represents an ellipsoid, surface of an ellipsoid, right? Okay, so this will be our equation number 1. Now we have got three arbitrary constants A, B and C. Okay. And to eliminate three arbitrary constants, we need four equations, right? So the first of the four equation will be this relation, right? So this is our equation number 1. Fine. Again, we have three variables, x variable, y variable, and z variable. It means two of the variables will be independent variables, and the third one, z, will be dependent variable. So let us first take partial derivative. So we are taking PD stands for partial derivative with respect to x variable, right? And this is implicitly defined function. So how will we take this partial derivative? We will do it like this: partial derivative, taking partial derivative both sides. So this one will be x square by a square, y square by b square, z square by c square equals to partial derivative of constant 1 with respect to x, right? Now how to find a partial derivative of the left hand side with respect to x? This diagram will guide us. Now z here is dependent variable and x and y are independent variables, right? So when we take partial derivative with respect to x, we will treat x and y as independent variables and z as dependent variable, right? So partial derivative of x squared over a squared with respect to x, this will be 1 over a square come outside. Derivative of x squared with respect to x, it will be 2x, right? Now partial derivative of y square over b squared with respect to x, well, b is constant. Again, when we take partial derivative with respect to x, y will be treated as a constant. So b is already a constant, y will be also treated as a constant. So partial derivative of y square over b squared with respect to x, it will be 0, right? Now, how to find partial derivative of z squared over c squared with respect to x? Now here c square is a constant, so 1 over c square come outside. We can't treat z as a constant because z depends upon x. Okay, so we'll take partial derivative of z square with respect to x. We will apply chain rule. So first z squared power rule, it will be 2z, and then derivative of z with respect to x, it will be del z over del x, right? And this one is constant function, its derivative will be always 0. So we'll further simplify it. We have this 2 as a common factor, so we'll divide throughout by 2. So we get x over a squared plus z over c squared del z bar over del x equals to 0. and this is our equation number 2. So this one was equation number 1, so we got equation number. Okay, so next we will take partial derivative with respect to y. But rather than going through all these exercises, we will use similarly, by taking partial derivative with respect to y. What will we get? In place of x, there will be y variable, so we'll get y, and with y we will have b squared. So we'll get y over b squared plus z will remain same, z over c squared, and we will have del z over del y. This one is equals to 0. So this one will be our equation number 3. Fine. So we have got equation number 1, equation number 2, equation number 3, but we have three arbitrary constants, and we know that to eliminate these three arbitrary constants, we need four equations. So we need one more equation. So to find the fourth equation, we will take second order partial derivative. Okay, now we have three second order partial derivative. One is with respect to x, del square over del x square. Another possibility is del square over del y square, and the third one is mixed derivative, partial derivative with respect to x with respect to y. Okay, now we will opt for the mixed derivative. Why? We will learn its advantage later on. As of now, either we take partial derivative of 2 with respect to y to get the mixed derivative, or partial derivative of 3 with respect to x. So we are taking partial derivative with respect to y, taking partial derivative of equation 2 with respect to y variable. So again, this is equation 2 is implicitly defined, so this will be del over del y of x over a square plus z over c square del z over del x equal to partial derivative of 0 with respect to y. Okay, again, we have the same diagram. Okay, z dependent variable, x and y are independent variable. Partial derivative of x over a squared with respect to y. When we are taking partial derivative with respect to y, x will be treated as a constant, so this entire first term become constant. So this partial derivative with respect to y of x over a squared will be 0. This one is plus z over c square del z over del x, right? So z is also a function of y. Its partial derivatives will be also function of y. So here 1 over c square comes outside, 1 over c square, and this will be partial derivative of z multiplied by del z over del x with respect to y. Okay, and the right hand side will become 0. Fine. So next we have to find this partial derivative. Z depends upon y, this partial derivative depends upon y, so we will have to apply UV rule. Fine. So 1 over c square is outside. Partial first function z as it is. Partial derivative of del z over del x with respect to y. So this will become second order mixed derivative. Then plus second function as it is, and partial derivative of z with respect to y, this will be del z over del y, and this one is equal to 0. Okay, now we multiplied throughout by c square, and this becomes z del square z over del x del y. We know that in mixed derivative in general the order does not matter, and plus del z over del x multiplied by del z over del y equals to 0. This is our equation number 4. But it's very good that the equation 4 does not involve any arbitrary constants. So this is the required partial differential equation, right? We, like example one, we don't have to do substituting a b c into equation number 1. Already while taking this partial derivative with respect to y, only all the rest of the arbitrary constants have got eliminated. So this one is the required partial differential equation. So before we move to next example, let us see the advantage of the taking mixed derivative. Suppose had we taken a partial derivative of 2 with respect to x, this a would have remained here itself. So elimination would have become a difficult exercise. Okay, so whenever we have to take the second order derivative to eliminate the constants, always first opt for the mixed derivatives. So example number 3, form the differential equations of the spares whose centers lie on the z-axis. Right. So this example is different from example 1 and 2 because here the relation between x, y, z variables are not given. Okay, so let us first form that relation between these variables. And how to find that relation? Okay, the information is given in the statement itself. Form the differential equations of all space whose centers lie on the z-axis, right? Now, we know that a sphere with the center ABC coordinates and radius equals to r. Its equation is given by x minus a whole square plus y minus b whole square plus z minus c whole square equals to r square. These are coordinates of center of the space, right? All these a, b, c and r, they are arbitrary constants, right? But we are looking for differential equation of those spheres whose center lie on the z-axis. Okay, so if the center is lying on z-axis, in that case, the x coordinate of center will be 0, y coordinate of the center will be 0, right? So in this relation, a will be 0, b will be 0. So the required equation of spheres will be x square plus y square plus z minus c whole square equals to r square, right? So this is the required relation between x, y, z, and we are now left with only two arbitrary constants, c and r. So this is the required relation between x variable, y variable, and z variables, right? And these c and r are arbitrary constants. So this is our equation number 1, fine. And to eliminate two arbitrary constants, we need three equations. Fine. So, as we did in example 1 and 2, first of all, we will take partial derivative with respect to x variable. So, again, this is implicitly defined relation. So, del over del x of x square plus y square plus z minus c whole square, this is equal to partial derivative of r square. Again, we have this diagram. Z is dependent variable, x and y are independent variable. When we take partial derivative of z with respect to x, y will be treated as a constant. So x square's partial derivative with respect to x, it will be 2x. For y square, it will be 0. Z is dependent variable, so we will apply chain rule here. Z minus c whole square is partial derivative with respect to x. This will be 2z minus c multiplied by partial derivative of z minus c with respect to x, chain rule. Okay, so this one is del z over del x, and r is constant, so this partial derivative will be 0. Again, 2 factor is common throughout this expression, so we'll divide this equation by 2, so we get x plus z minus c del z over del x equal to 0, and this is our equation number 2. Again, we will use the tool at our hand, that is similarly taking partial derivative with respect to x, beg your pardon, with respect to y. So similarly, okay, we will get in place of x, we will get y. So this will be y plus z minus c. All the x variable will be replaced by y here because of the pattern. And this is equal to 0. This is our equation number 3. So since we have only two arbitrary constants, okay, and we already have three equations at our hand, so we do not require higher order partial derivative. Now we have to eliminate R and C from equation number 1, 2 and 3. How will we do it? Okay, so one way of doing it is, right, in expression 2 we can write this equation 2 as x equals to minus z minus c del z over del x. Equation 3 we can write as y equals to minus z minus c del z over del y. Okay, now we divide left hand side by left hand side, right hand side by right hand side. So this minus z minus c factor minus z minus c factor will cancel out, and that way we have eliminated all the arbitrary constants. Okay, and we will cross multiply here. We will get x del z over del y is equals to y del z over del x, and this is the required differential equation. We can rewrite it as y del z over del x minus x del z over del y equals to 0. So this one is the required differential equation, and it turned out to be a first order partial differential equation. Okay, at times we write del z by del x as p by p notation, del z by del y by q notation. So this becomes yp minus xq equals to 0. So we can write this differential equation in either of the form, either this in terms of the partial derivatives or in terms of symbols p and q. So in this video, with the help of 3 examples, we learned how to form partial differential equations by eliminating arbitrary constants. Thank you.